Welcome to Mastering Solutions. This question is a little tricky just because it forces us to pull back some information from previous chapters. But really what this is it's a circular aperture question. This antenna that they're talking about, this is acting as the diffraction, the circular aperture through which these microwaves are getting diffracted out. And so at 30 kilometers, we have to figure out what's the diameter of that. So you can think of it as we're going to find the width of the central maximum and use that as the boundary for how far the diameter is of what we're looking at. And so to do that, we know that we can use the equation W, which is for the width of the central maximum, and 2.44 lambda L over D. And it's already set up for what we're looking for. So when we look through the question, L in this case is the distance, and that's 30 kilometers. So from our aperture, the antenna, out to where we're looking at it. So at 30 kilometers, that's going to be 30 times 10 to the 3 meters. So now we have that in standard units. We also know that the antenna is a 2-meter diameter circular antenna. So D is equal to 2 meters. We're told that the wavelength is, and don't get caught by this, don't put in this. This is the frequency, right? So this is one of the things where we have to go back to previous chapters. Lambda is equal to the velocity over the frequency. And in this case, since we're dealing with microwaves, that's on the electromagnetic spectrum. So the velocity will be the speed of light. So we have C over F, and that's 3 times 10 to the 8th meters per second over the frequency, which we said is 12 times 10 to the 9 for gigahertz. So the wavelength will be 3 times 10 to the 8th divided by 12 times 10 to the 9, and that gives us 0.025. So lambda is going to be 0.025 meters. So now we have everything that we need to plug in to solve for A to figure out the diameter for the central maximum at 30 kilometers. So W is equal to 2.44 times lambda, which we said is 0.025 meters, times L, which we said was 30 times 10 to the 3 meters. All of that gets divided by D, which we said is 2 meters. So now when we go to our calculator, we have 2.44 times 0.025 meters times 30 times 10 to the 3 meters. And then that gets divided by 2 meters. So we have 915 meters. That is the width of the central maximum at 30 kilometers, or the diameter of the radar beam. Now for part B, we have to figure out the intensity at that distance. And so this is kind of tricky because I know this was in a previous chapter, but remember the formula for intensity is I is equal to power over the area. And in this case, the power is going to be, they tell us 100 kilowatts. So 100, and we need this in watts, so kilo is 10 to the 3 watts. And what's the area? We're dealing with a circular area, so that's going to be pi r squared. And so when we plug this in, we have 100 times 10 to the 3 watts divided by pi. Now, don't plug in the 915 meters because that's the diameter. So we need 915 over 2 squared. Now we can plug this in. So we have 100 times 10 to the 3 watts divided by pi times 915 over 2 squared. And that gives us 0.15 watts per meter squared. So we have 0.15 watts per meter squared for the units for intensity. So that's our answer. At 30 kilometers, we have a diameter of 915 meters and an intensity at 0.15 watts per meter squared.